that's about it. Can you do... There's a community thing. Announcements, concepts, challenge, coding challenge, feature requests, demos, physics. What's the next time? Okay, the quantum computing concepts, they are also too technical in terms of... Okay, no, but I mean, this is just random questions. What is chain, blah, blah, blah. Okay, no, not interesting. Not interesting. Learn about Leap and QC, run a demo, watch videos, meet DWave customers, and maybe that. Maybe we'll do that. Let's see what's in here about Leap. So there's the video that we sort of an introduction video. Okay, some case studies. NASA quantum assisted unsupervised machine learning for digit recognition. Those are articles. I've read about that, I remember. About quantum computing. What is quantum annealing? Getting started with the DWave system documentation, DWave lab tour, customers using DWave, Google and NASA's Quantum Artificial Intelligence Lab, USC Center for Quantum Information Science, quantum computing at the USC Lockheed Martin. Okay. Published research. Let's take a look at this one. Seems like a good one for me to...
Quantum computing, although being a relatively young field, is actually quite complex, and there's many different approaches
How long is that?
being pursued around
6
the world
minutes.
for building a quantum computer. At DWave, our approach is quantum annealing, and in this video I'll explain what that is and how it relates to the other forms of quantum computing. So quantum annealing is basically a way of using the intrinsic effects of quantum physics to help you solve certain types of problems called optimization problems, and also a related problem called probabilistic sampling. Now let me explain what these are. So an optimization problem is a problem where you are trying to search for the best configuration.
Yeah, okay, I'm not gonna...
You're trying to build a house. You've got a fixed budget to afford them all.
Explain that stuff.
So fit in and it's not... You can frame them as a type of problem called an energy minimization problem.
Energy landscape.
And like a fundamental part of physics is that everything's always, or quantum physics problems are related to optimization problems. But what you're trying to do is sample from many low energy states and try and characterize the shape of your energy landscape. This is useful for application areas like machine learning, where you're trying to build a probabilistic representation of the world. And these samples give you information on machine learning, on techniques to solving these kinds of problems. So that's a description of quantum annealing and the kind of things it's used for. So how does it relate to the other forms of quantum computing? Well, the first form of quantum computing that was developed is called gate model quantum computing.
This gate model quantum computing is what the IBM Q Experience guys are doing.
And the differences between these two kinds can be summarized as follows. So in quantum annealing, what you're trying to do is harness the natural evolution of quantum states, although you don't have any control over that evolution.
Okay.
So you set up the problem at the beginning, you let quantum physics do its natural evolution, and the configuration at the end corresponds to the answer you're trying to find. In gate model quantum computing,
I like
the aim is a lot more ambitious. What you're trying to do there is be able to control and manipulate the evolution of that quantum state over time.
Okay.
Now this is a lot more difficult because quantum systems tend to be incredibly delicate to work with. However, you can having that amount of control means that you can solve a bigger class of problems.
So you're basically saying the gate one, which is what other people are doing, is way more complex and complicated. So, and annealing is easier. And so, what you decided to do annealing. I mean,
So these differences are the reason why it's been possible to scale up quantum annealing processors to over 1,000 qubits now, whereas the state of the art in gate model quantum computing is around 10 qubits. So it's technically a lot more difficult to get the qubits to work together coherently in a gate model quantum computer. However, there have been some very powerful algorithms developed for use when they reach scale. So a couple of examples are...
okay, so we know now. So at least we know the difference between those two types of quantum computing, the gate model and the annealing model. And just because of the analogies that he's just putting in this video, seems like the gate model is way more powerful in terms of what things could you potentially do. And I think that's really what I'm going to spend the rest of my time focused on. So it was nevertheless interesting. So and that's what I thought, right? So the quantum annealing is basically just one really specific way to solve problems, because it just so it just is nothing. Literally, it harnesses the evolution, the natural evolution of a quantum state or a quantum system, so to say. And because naturally we believe things tend to go to the lowest energy levels, then if you formulate your problems this way, then you're going to find the solutions that you want if you define the problem the right way.
Shor's algorithm for factoring large numbers, and also Grover's algorithm for...
Yeah. So both I've read about both algorithms before, and I definitely will actually try to deep dive into those. But this is from the gate model type of quantum computing. So the Shor's algorithm is the algorithm for factoring, and Grover's algorithm is an algorithm to, if I remember well, is to find one item within a list way faster than you would with a classical computer, where you, in the worst case scenario, have to go through each of the elements of the list to find that element that you're looking for. And those are really, again, they're also really purpose specific, but I have the intuition, I have the impression this is where the potential is. This is where really, making sure that there's many people in the industry, there's many people that learn quantum computing, and at least the gate model. This is where I think the technology can explode, and that's why I really want to learn that.